Hi everyone, welcome again. Our weekly seminar at Lyon. Our speaker today is Nicolas Bousquet from Lyon. So I learned to know Nicolas from a number of his nice papers in structural graph theory. One I have in mind, I think the first one I had is your result about Erdős-Hajnal property for paths and antipaths, yes? So the result there is that if you have graphs with no induced path and no induced path in the complement, we fix the size of the path, then you must have a polynomial click or anti-click in your graph, yeah? And that's, it's not only the result, but it's the paper is 2 or 3 pages long, right? And it's fun even for a student to read. Yes, and more papers in this spirit. But now when I was looking you up before the seminar, I see that one of your favorite topics as well is reconfigurations, graph reconfigurations for problems. Yes, so welcome, Nicolas. Please, the floor is yours.
Thanks a lot, and thanks for the invitation. So today I'll speak about something that is neither structural graph theory, neither reconfiguration. It's local certification. So that's a topic I just learned this year working with Laurent Feuillet, who is currently a postdoc in our team. And we worked on it with Théo Piron, who is assistant professor in Lyon too. So before going to local certification, so yeah, first I want just a disclaimer. So all the graphs I will consider in this talk are connected. Basically, we are imagine in a distributed world. And so if your graph is disconnected, that does not make any sense. So everything is at all time connected. Okay, so before going to certification, I'd like to start with maybe distributed algorithms. Okay, so usually, and by usually I mean for people of graph theory, structural graph theory, or centralized algorithms, we always assume that we have the whole instance and we want to optimize and solve our problem. So we will have to change a bit our point of view today and look in a distributed way to things, and imagine that you are a node of a graph like this vertex, and you want to 3-color the network. So you want to 3-color your graph, okay? And so which color do you have, can you choose in order to be sure that you have a proper coloring? Okay, that's hard at this point because you just have no knowledge of the graph, okay? So what you can do is in one step, you can look at your neighborhood and you have access to all your neighbors. So you don't know how they are connected together. That's why I put this dashed line there. And so can you 3-color the graph? So probably still not. You have to go to look further. And so the question in distributed algorithms is how far do you have to look at to be sure that you can 3-color your graph or that it's impossible? Okay, so that's the main question in distributed algorithms somehow, is up to which distance do we have to look at to take a correct decision? And so here correct means so every node choose a color at the end, and we must have a proper coloring. So adjacent vertices must receive distinct colors. Okay, and so now we will look at something that is heavily related today, that is certification. Okay, so what is certification? So imagine now that you have colored your graph, so your node knows its color.
Nicolas,
and you want...
one question.
Yep, true.
There must be something standard, but what do you do if every vertex is the same? Like, I don't know, like a cycle?
Yeah, okay, so that's a good question. So basically, we assume that all the nodes have some IDs. Okay, so you can distinguish them, but basically, if you have a cycle and you want, for instance, yeah, so that's complicated that's not easy to color a cycle, but yeah.
Okay.
But yeah, you assume that all the nodes have IDs, so, or that you have a randomized algorithm, and then if you are randomized, you can just in a few steps just guess the IDs for all the nodes that are distinct. Okay, and so now imagine that you have your network, and so you have a coloring, and you want to check it. So now the question is much easier for coloring, because you just have to look at distance 1, look at the color of your neighbors, and basically check that the colors of all your neighbors are different from yours. And if all the nodes do that, and all the nodes check that their neighborhood are disjoint, they can all say yes. And if everyone say yes, we can say, okay, that is a proper coloring and we are happy. Okay, so in other words, it means that if we give to every vertex a label that corresponds to their colors, in the future, whenever we want, we can check that this coloring is still proper, and we can check that everything is fine. Okay. And so that's basically what is certification about. So certification is something like, okay, maybe we will make some computation and we find some results. And maybe in the future, we will like to check again that this property is still satisfied, because maybe our network will have some modifications, or some edge will disappear, some edge might appear, and we want to check that the property is still satisfied. Okay. And so the question is, which certificate do we have to put on the vertices to be able to check later on that the property is still satisfied? And the goal will indeed be to minimize the size of this certificate. Okay, so more formally, so we will have a graph where every vertex has a unique ID in one n, and n is the number of vertices. So, and basically for free, we can assume n to the c for some constant c if we prefer. And every node will have a certificate. And the certification algorithm, so that will be something that every vertex will make on its own. It will read its certificate and the certificates of all its neighbors. It will have an infinite power of computation. So basically, the problem is really that you can only look locally at what happens, but your power of computation is infinite. So okay, so now you just make all the computation you want with your certificate and the certificate of your neighborhood. And finally, you have to accept or reject. Okay, so that was a certification algorithm does. And we say that a property, so for instance, I don't know, 3 coloring can be certified with f of n bits if if your property is satisfied, which means that you have a valid 3 coloring, you are able to give a certificate of size f of n to every vertex so that all the nodes accept. And if your property is not satisfied, so your graph is not 3 colorable, then at least one node rejects for any possible certificate assignment. Okay, so for coloring, that's easy to do that. You just give a 3 coloring to your graph if it's 3 colorable. And if it's not 3 colorable, anyway, some vertex will have in its neighborhood a monochromatic edge, and this node will reject. Okay. So now there is a question that is natural, that is, what can be certified locally? And the answer is easy, it's everything. So you can certify locally everything. So maybe you think that the problem is not interesting, but actually I'm a bit cheating when I say that, not cheating, but you can certify everything, but you have to pay a price for that. You have to pay a price of, in terms of size of the certificates. You can certify everything with certificates of size n square. Okay, why? Because you just give to all the vertices the whole graph, the ID of each vertex, and so it just check that according to the adjacency matrix and its own ID, its neighborhood corresponds. And now, since it has the whole graph and the infinite power of computation, it can check if the property pi is satisfied or not. Okay, so now the real question is not, is it certified locally, but can we improve this omega of n square, so this n square in general? And on the other hand, can we give some lower bounds on the certification? So for coloring, for instance, 3 coloring, we can certify it with just 2 bits, because we can just give with 2 bits the color of each vertex. But for most of the interesting problems somehow, which do not have some trivial certificates, usually you can prove that there is a lower bound of size omega of log n in terms of size of certificates. So why log n? Because basically that's the size of an ID of a vertex. Okay. So can we really improve this omega of n square? And the answer is negative. We can do it in general. And so there is this result of Goose and Sumuela. We prove that for non-trivial automorphism, so the existence for given a graph, the existence of a non-trivial automorphism for this graph, you need omega of n square bits to certify this property. And so the idea is the following: basically, imagine that you have two graphs that are just connected by an edge. Okay, and so now if these two graphs are the same, you have a non-trivial automorphism because you can just switch the two parts basically. And so in order to check that, somehow what they prove, the intuition of this proof is that in order to check if H1 is equal to H2, you basically have to give to the node of H1 incident to the graph H2 and the node of H2 incident to the graph H1 the information of what is this graph H1 and what is this graph H2. And basically the number of graphs is 2 to the n square, and so you can't avoid omega of n square, because in order to represent all this all the possible graphs H1 and all the possible graph H2, you need this number of bits anyway. Okay, so that's the intuition of the proof. So the proof is indeed technical, and I don't want to enter into details, but that's the basic intuition of why you need this n square. And also there are other properties that can be certified with few bits. For instance, diameter 2. So do you graph of diameter 2? You can certify it with omega of n bits. So that maybe seems a bit surprising, because you think, okay, I just look at distance 1. By just looking at distance 1, I cannot even determine if my diameter 2 is 2. So that's a bit crazy, I think. But there are some properties that needs a lot of bits to be certified. And basically today we will have two research directions. Okay, yeah. So two research directions. The first one will be, okay, what can we certify with few bits, and by few I mean big O of log n, basically. And another research direction, which will be, okay, how do I have to restrict my graph class to be sure that I can certify a lot of things, or basically everything, with few bits? Okay, but before going to that, I want to explain a bit how we can certify spanning trees. Okay, so there is this result of Corman and its co-authors that shows that spanning trees can be certified with big O of log n bits, not round, of course, bits. Okay, so how can you do that? So let's try to do it in a way to let's try to build certificates, and when we find some mistakes in it, let's try to correct that.
What does it mean to certify spanning trees?
Okay, so okay, good question. So it means so you want to basically select some edges that form a spanning tree. Okay. So imagine, for instance, that you have this spanning tree and you want to certify it. So you can say, okay, every node might receive its parent ID. Okay, so for instance, for this top node here, I just assign this node that is parent ID. And for the root, I just give it its own ID. But you can cheat the system if you do that by just, for instance, making a cycle and some arborescence on it. And here, all these nodes receive their parent's ID, but you just cycle there. Okay, there is no root on this graph there. Okay, so that's not working. So now you can say, okay, why it's not working? Because basically I can cycle. So what we can add is, let's add the distance to the root for every vertex of the graph. Okay, so we have this spanning tree now. And so we have the root that is at distance 0 from the root, then all the people that sees the root that are at distance 1, and blah, 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 and blah, blah, blah. But again, if you do that, you do not necessarily obtain a spanning tree, because you might have several connected components. Okay, so here, basically, we have two arborescences, and not just one spanning tree. So you just have a spanning forest somehow. And so what is the solution to that? You just say, okay, now every node of the graph receives the ID of the root, okay? And now we are sure that we know that all the nodes will agree with the certificates, because now if two different nodes receive a different ID from the root, that are two different vertices that are adjacent, they can reject. Okay, and since the graph is connected, we know that all the vertices receives the same ID for the root, and basically we know that we have this arbor sensing. And so that's interesting to certify spanning trees like that, because basically in many cases we will be interested in just broadcast some information to the roots, and so all the vertices will just go to the root, and the root will just make a final verification to check everything. So okay, so first research direction is which kind of properties can be certified with big O of log n bits. So we have seen that for k-colorable graphs, we can make it in even less than that. We can do that in log k bits. But we can certify many graph classes actually with big O of log n bits. So that was initiated by Laurent and some co-authors. And so they obtained this very nice result in 2020 that planar graphs can be certified with log n bits. It can be extended actually to banded genus graphs. So there are two proofs of that. And there are actually many graph classes now that are known to be certifiable with big O of log n bits. For instance, interval and chordal graphs. And Laurent, when he arrived in our team for the postdoc, asked us the following question. He left open in several papers: is it possible to certify H minor free graphs with big O of log n bits? Okay, so what I thought at the beginning, I was pretty optimistic, because I really thought that we know quite well what are H minor free graphs, so it should be easy. But actually, I realized that we don't know quite well H minor free graphs. We just know some properties of H minor free graphs. So basically, when we design usually algorithms, what we do is, okay, imagine that we are H minor free. So we know that this property is satisfied, and then we can derive an algorithm. And most of these properties are easy to certify, but the problem is that they do not characterize at all H minor free graphs. Okay, so we really have a problem, because in general, that's really hard to exactly understand what is a H minor free graph. And so we really have some very partial results towards this direction. We show that H minor free graphs can be certified with log n bits if the size of the graph H is small. But basically, that does not really give any intuition general conjecture, in the sense that we really used all the machinery of graph decompositions, because all this H minor free graphs for small graph H, we have some strong decomposition theorem. And basically what we were able to do is really to transform this decomposition theorem into certifications. And so that's hard to imagine that in general, we have a nice decomposition theorem for H minor free graph. So we really are completely blocked in general of how we can really certify H minor free graphs for the general case. But in order to prove that, we got a couple of nice results, I think, on the way, because basically we proved that many of these structural results of graph theory can be actually be transformed into certificates with log n bits. So for instance, we show that we can certify that a graph is 2 or 3 connected. We can certify the block cut tree decomposition, and we develop a couple of new tools in order to prove these results. And I think that much more than the result by itself, it's really all the small pieces of certification we developed that are interesting, I think. And so the second line of research we investigate is on which graph class can we certify many things locally. And so, in other words, and very informally speaking, our goal was to obtain some kind of analog of Courcelle theorem for certification. Okay, and what we proved is actually that tree depth is a good graphs of bounded tree depths are good class of graph for this thing, because basically we can prove that every MSO formula can be certified with big O of log n bits on bounded tree depth graphs. And we can also certify that a graph has bounded tree depths, which I think is really important, because if you can certify a formula on bounded tree depth graph, but you can't check that your graph is bounded tree depths, it does not really make any sense. Okay, and so now in the rest of the talk, I will explain a bit what we did in these two research directions and ask you many questions, because basically we answered a few questions, but probably we didn't succeed to answer most of them. And I want to share some of the questions we have still left open. So for this first line of research, I don't want to give you the whole proofs of everything. I just want to illustrate it on some example, which is the certification of K4 minor free graphs. Okay, so first of all, what we proved is this result, that is, if you have a graph H that is two connected, which is the case for K4, then if you can certify two connected H minor free graphs with big O of log n bits, then you can certify H minor free graphs with big O of log n bits. And so the idea of the proof is the following. So basically, imagine that in your graph, you have a model of H, so a model of K4. Then basically all the vertices of, you can assume that all the vertices of this model belong to the same two connected component. Because if there are vertices in another connected component, you have a cut vertex, and basically you can remove vertices of one of the two sides. And so the idea is to certify the block cut tree. So what is the block cut tree? Basically, you have blobs that correspond to the two connected components, and you have vertices that are the cut vertices of your graph. And so you have this. And what we can do is certify this block cut tree. And how can we do that? Actually, a bit as we certify trees. The idea is to say, okay, one of the components will be the root of my tree, block cut tree decomposition. And I will just make the certification of tree I presented you. I can do it again here on this block cut tree decomposition. And now, instead of just having one vertex, we have one blob. And we just say to all the vertices of the same blob, okay, you belong to that blob that is labeled, I don't know, 1, 2, 3, 4, blah, blah. And you just have to check that all the vertices are of the same blob agree on the same parent, and that one of them really has one parent. So one of these vertex really has some neighbor in that blob. Okay, and so you can certify basically this as you certify trees with a bit more technicalities. Okay, and so there is a technicality, for instance, that is that does not happen with trees, which is, okay, this vertex, actually it belongs to many, it can belong to many two connected components. So this one belongs to this one, but it also belongs to these two connected components, these two connected components. And you can attach as many, imagine that you have a flower, you can attach as many two connected components as you wish on the same vertex. And you don't want that this vertex receives certificates of all these two connected components, because otherwise it will just take as a certificate the union of the label of the certificates of the two connected components, and that will be too much. And basically what we were able to prove is to show that we can certify actually in a pointed way a two connected component, that is one of the vertices might not receive any certificate if we wish. And so that permits to be sure that we do not put too many certificates on the nodes of our network. Okay, and so then we just have to certify that two connected components are indeed two connected. So when we just give to the vertices that are there, we just gave them the same label. We say you are in the component 1, for instance. We have to check that all the vertices that are supposed to be in the component 1 are really in a two connected component. And finally, in order to finish the proof of this lemma, we just have to give to each two connected component the certificate we assume to have, which is size log n, and that gives the certificate of H minor free graphs in general. Okay, so that's the idea of the proof of this lemma. So I explain you the idea for the block cut tree. Let me explain you how we can certify that two connected components are really two connected. And to do that, we will use the very standard equivalent definition of two connected components that you graph as an ear decomposition. So what is an ear decomposition? Basically, it means that you can enumerate all the vertices and all the edges of your graph in the following way. You start from a cycle, any cycle in your graph. And now you can add airs. So what is an air? So it's just a path between two already existing vertices, okay, that are not the same. So here you add, so here at this step, you add a path between these two vertices. And then at the next step, you can add this path. And then at this step, you can add this path. And maybe you have some edges at the end, and you just add edges that are just paths of length 1 between already existing vertices. And that is completely equivalent to two connected graphs. So you graph as an ear decomposition if and only if it is two connected. And now the question is, how can we certify ear decomposition? So we will make exactly the same. So we'll start from the cycle and we will certify the cycle. Okay, so how can we certify the cycle? We will just pin 2 points of this cycle and say, okay, we have two paths between these two vertices, and that are these paths. Okay, so we can just follow this path in the direction, and we will say to the vertices of this cycle, we will give them label 1, which means that you were in the first ear somehow of your decomposition. And when you add the second ear, you just say, okay, I take a vertex, another vertex, I can now have my my ear like that. All the vertices that are created there are labeled 2, and I check that I have this path, and the endpoints of this path are labeled with some label that is smaller than 2. Okay, so these two endpoints are labeled 1. And for every error, I can do that. And finally, I end up with my wall graph, and I know that it gives me a certification of my ear decomposition. Okay, so that's how you certify two connected components. Okay, so now let's go back to K4-free graphs. And to conclude the proof for K4-free graphs, we have this theorem due to Epstein, which says that a two connected K4-free graph, K4 minor free graph, is a two connected series parallel graph, which is a graph that is a nested ear decomposition. A nested ear decomposition is basically the same as ear decomposition, except that you add more constraint on the type of ears you can add at each step. Okay. But what we proved is that we can again give a certificate for this nested ear decomposition, and so that guarantees that we can give a certificate for two connected K4 minor free graphs. And finally, we just use this lemma to guarantee that we have a certificate for K4 minor free graphs. Okay, so this example of K4 minor free is really typical of how we did the certificates for this H minor free graphs for small graph H. But I think that more interestingly, the question is, what can we do next, and what we didn't succeed to do? Because I think that there are a couple of really somehow interesting questions to look at. And so the first one, so what was our initial plan, and what did we try with small graphs H at the beginning? We thought, when we were really optimistic, that maybe we can opt for an inductive proof of this result. So assume that we can prove it for all the graph of size 4, then maybe we can take a fifth vertex and attach it to a graph of size 4 and try to prove that if we have a certificate for this graph H, we can extend it to this graph of size 5 and so on and so on. And the first step to do that will be, okay, assume that you have a certificate for H minor free graphs. Are you able to give a certificate for H plus K1? So you just have an isolated vertex in your minor, H plus K1 minor free graph. And we were, so I really spent a lot of time trying to prove that. I was completely desperate because I really thought that it should be easy, but actually it's not. And I think that actually this question is maybe a bit deeper than what it appears to be, because it's somehow related to okay, minimal counterexamples somehow. Okay, so for instance, imagine that you take a vertex minimally non-planar graph. So what does it mean? It means that this graph has a K5 or a K33 as a minor, but it does not have a K5 plus K1 or a K33 plus K1 as a minor. Okay, so somehow this question is essentially saying, okay, can you imagine that you can certify a graph class? Can you certify minimal graphs that do not satisfy, that do not belong to that graph class? And I think that in general, that is not that easy, and that's maybe why we didn't succeed. And so, for instance, we know that we can certify planar graphs, and I have no clue if we can certify minimally non-planar graph. I think that's an interesting question. And another question we didn't succeed to solve is the following. So, can we certify F minor free graphs for any forest F? So that, I think that is a simplest question. And again, that might be a first way to try to prove the conjecture somehow, is try to start with graphs that are really sparse, and then try to increase the density and try to understand when things starts to be complicated. Okay, so that's the next first set of questions I wanted to ask. Another pool of question is the following. So in many decomposition algorithms, somehow for small graph classes, we have this SPQR tree which appears, and there are somehow let's say some kind of generalization of block cut tree for three connected graphs. So what is a SPQR tree? So very briefly and informally, so you have so a partition of your graph, so your graph is there, and you will partition it into blobs of types S, P, Q, and R, where S means you have a cycle of length 3, P you have a multigraph with 2 vertices and at least 3 edges, Q just one real edge, and R means that you have a 3 connected component. Okay, and so now the question is, can we certify SPQR trees partition? So we are not far from being able to do it, because we can certify S, a P, a Q, and a R component, because we know how to certify a 3 connected graph. We know how to certify that a graph is a single edge. We know how to certify that we have a multigraph. We know how to certify a cycle. But the problem is that that's not easy to certify really SPQR trees partition, because here, for instance, in this graph, in this cycle S there, what you remark is that this edge of the cycle is actually not a real edge of your graph. Here you don't have any edge. This edge just simulates the fact that you have a path in R. Okay, so when you have a cycle like this, basically, it might mean that you actually have something like that in your graph. Okay, but that's not a problem, because we can simulate the fact that we have this edge by this path. Okay, we can just broadcast some information along this path from this vertex to that vertex to say, okay, outside this component, we have this path. But the problem is that maybe this edge again is not a real edge of your graph. And now you have to broadcast 2 information. So basically you have to broadcast the right information. So from this vertex to this vertex, you have a path, but you also have to broadcast this information from that vertex to that vertex. You also have a path. And maybe at some point, if you repeat that again and again, that will saturate the final edge here, because here you have you have to broadcast 2 information through this edge, but then 3, 4, 5, and so on and so on. And we were not able to find a way to ensure that we can just broadcast a limited number of information along the edges. And so we were not able to certify this SPQR trees. Another question, which I think is interesting, is what happens for K5 minor 3? So basically, we proved it for all the graphs of size 4. Everything is planar so far. So planar minors are somehow easier than general minors. So what happened for K4 minors? And we have this theorem of Wagner that ensures that K4 minor free graphs correspond to three sums of planar graphs and the Wagner graph. Okay. And so certifying planar graph, we know that we can do it. We know that we can also certify Wagner graph because they are just graphs of bandit size. So this point is easy. Now, what is a threesome? It just means that you glue graphs together on a click. Okay, so threesome means that you are just gluing these graphs on clicks of size at 3 in a tree-like structure. And so we know, again, using this kind of block cut tree, that we can certify all these block tree-like structures. Okay, so we have the feeling when we read this theorem that we can certify K4 minor free graphs, but unfortunately, we have the authorization after just gluing the graphs in this gluing operation to remove some edges of the click on which we glue them. And now we exactly end up with the same problem, which is, okay, maybe we have glued on this click, but now we remove these edges. So we have to broadcast some information along the graph to guarantee that when we glued it, it was a click, to be sure that if we glue it, so this graph 1 and 2 here on this click, that was a click when we glued it. And again, we have to broadcast some information, and we have no reason we didn't find a way to again limit the number of information that will go, which we'll have to pass through a vertex for that broadcasting. So again, we basically end up with the same type of problems with these K4 minor free graphs. And again, for K3 minor free graphs, there exists the same type of results for 2 or 3 sum of planar graphs and a couple of graphs. So again, we have the same type of problems there. And another question that is kind of independent, and I think of independent interest for people working on certification and distributed algorithm, which is, can we certify that the graph is K-connected with big O of log n bits, where this big O will probably depend of K, I guess. So we can prove it for 2 and 3, and basically we don't know for K, at least for if we can certify it. And I think that's also an interesting question. And probably for people from that field, that's maybe from all the questions I asked so far, the most interesting question, I will say. Because yeah, for the robustness of your network, you need, you'd like to know if your graph is evenly connected or not. Okay, so that ends the first part of my talk. So if you have any question, feel free to ask. Otherwise, I can go to the second part, which is this kind of weak analog of causal theorem. Okay, so before stating formally the result, maybe I should remind you what is monadic second order logic. So I will be very fast because I won't really use it for the rest of the talk. But basically, so for logic, you have the first order logic, which is you can only quantify on vertices and your predicate are adjacencies. So here, for instance, you can, this is a formula to say that your graph has diameter at most 2, so if it's satisfied. So for any pair of vertices, either they are the same or they are adjacent, or there exists a vertex such that Z is adjacent to X and Z is adjacent to Y, which means that your graph has diameter 2. So what you can notice, I told you that diameter 2 cannot be certified with less than n bits. So that means that in general, even very simple first order logic formula cannot be certified with log n bits. And then there is the monadic second order logic, which is basically the logic where you can quantify in the set of vertices for first, so MSO1, and edges for MSO2. And now the predicates are adjacency and membership. Okay. So I don't remember which formula I put there. So you have a partition into 2 sets. So this is 2 colorability probably. So there exists a partition into 2 sets. Every vertex must merge must belong to exactly one of the two sets, and for every edge, then you must be in different sets, which means that you have a proper coloring. Okay, and so for instance, extreme minor is MSO1, Hamiltonian cycle is MSO2, and so on and so on. So you have many problems that belong to monadic second order logic. And to be really informal, Kursel proved in the 90s that when you have a monadic second order formula, you can decide if it's satisfied in FPT time, so linear time. Okay, so in FPT time parameterized by the Triwitz, where the function of n is linear. Okay, and so there is now an important line of research that is interested in trying to extend this result to other classes and find some kind of equivalent or more general statement than this. So what will be our ultimate goal? We indeed did not succeed to reach. It will be to prove exactly the same. So every MSO formula can be certified with big O of log n bits unbounded Triwitz graphs. So that will be the ultimate goal. We don't know if it's true or not. I really have no strong opinion on that, to be completely honest. But what can I say is that even certifying that a graph has bounded Triwitz, that's not that simple. And basically, there are two issues for that. So the first one is that imagine that you have a 3D composition of your graph. So the problem is that the diameter of your bags might be arbitrary. And so maybe, again, you have to broadcast information basically in all the graph for all the bags, in order to say, okay, these vertices will belong to the same bag, and checking that they indeed belong to the same bag, you have to broadcast information. So that's a problem. And the second problem is that a vertex can belong to a lot of bags of your 3D composition. And you can just say then, okay, my vertex belong to that bag, that bag, that bag, and that bag, because maybe that's too much information. You will need more than log n bits to do that. Okay, so that's not completely hopeless, because, for instance, imagine, so I told you that chordal graphs, you can certify it with log n bits, and so you don't have the first issue, which is the diameter of the bag, because you know that the diameter is 1. But for chordal graphs, a vertex can still belong to a lot of bags of your 3D composition, of your click tree.
But I have a question.
Yeah, sure.
But these bags to which vertex belong, they are connected, right? So cannot you look at a total ordering which expands this bounded tree width and somehow say that it's like from here to here or something? I don't know, maybe not.
I'm not sure to understand, but for instance, in a cycle, so your tree width is 2, but your bags are not connected, because basically your vertex V1 will belong to all the bags, and then you will just have a bag with V1, V2, and then V1, V2, V3, V1, V3, V4, V1, V5, V4, V5, blah, 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 and Vn, V1. And you have to keep this V1 all along just to connect it with Vn.
Okay.
Does it make sense?
Yeah, I think so. Thanks.
You're welcome.
There are some nice 3D compositions, like what's the names, linked and lean 3D compositions, where whenever you have bags of size K and all the bags in between are of size at least K, then you have a linkage. And in one of the variants, you even have a linkage between any subset of size X here and subset of size X here. This gives you lots of connectivity. It's just a random thought, but maybe.
Yeah, maybe that's a good idea.
Yeah, sorry.
No. That's a good idea. Maybe we can try that. Yeah. And and there is a second issue, is that even if we assume that we can certify banded tree widths, we don't know how to do that. That's not clear how we can certify MSO formula. We don't have a strong idea.
Do you know how to certify bounded path width?
So yeah, we know how to certify banded passwords. No, we know how to certify banded tree depths. No, banded. I don't know. We didn't try actually.
Okay.
To be honest, we didn't really try it.
Okay.
And so basically we went to this depth that is easier to manipulate for us. That is tree depths. And so what is tree depths? Basically, you will put the vertices of your graph on a tree, on a rooted tree, and now every edge should be between a vertex and one of its ancestors. Okay, so here for K4, you have 4 levels, 1, 2, 3, 4, and every vertex is connected to one of its ancestors. And the tree depth of the graph is a minimum depth of such a tree. And one the advantage of tree depths is that we have no long pass. So basically, we wanted to be sure that we have not this issue of very long pass and kind of bags of huge diameter. And so we went back to tree depths to avoid this problem that can still appear for pathways. And so in the zoology of depths, so the tree width is smaller than the path width, that is smaller than the tree depths. And so as I told you, the advantage of tree depth is that the diameter is banded. And we also have these nice results, which ensures that for every graph of banded shrub depths, and shrub depths generalize somehow tree depths, we can construct a kernel that satisfies the same FO formulas. Okay, so what does it mean? It means that so Gajarski and Eleni, what they proved is for every graph of banded shrub depth, you can basically construct a smaller graph that satisfies the same FO formulas. And informally, what they also showed is that for banded shrub depth and so tree depths, FO is equivalent to MSO somehow. So what you can express with MSO, you can find an equivalent FO formula that exactly says the same. Okay, and so what we did is that we proved that we can certify tree depths with big O of k log n bits, and we proved that every MSO formula can be certified with big O of k log n bits. So let me try to give you the intuition of that result. So imagine that you have your tree depth partition like this. So basically the idea is to say to every vertex, I will just, so this is my tree here, I will just give to each vertex the list of ancestors of that vertex, okay? So for 3 here, its 2 ancestors are 1, 2, for 4 it's 1, 2, for 2 it's just 1, and for 1 we have no ancestor, and so for 5 it will be 1 again, and so on and so on. But if you do that, actually you can again cheat a bit the system, and basically you can cheat because here there might be a non-edge between a vertex and its parents, and because of this non-edge, you might have some trouble. And so in order to solve that problem, what we have to do is to say for any vertex, so for instance here for the vertex 2, we will have, so we can assume that the subtree rooted on that vertex is connected. So we can assume that the subtree rooted on 2 is connected. We will take a spanning tree of it that is rooted on a vertex that sees the parent of 2, so here 1, and we will certify this spanning tree. And somehow that will permit us to avoid the problems here because of this non-edge, because this vertex 3 will actually just check that 2 and 1 really agrees on their list of ancestors. And so we do that for any subtree. So we'll do that for the subtree, for the tree 1, so rooted in 1, rooted in 2, rooted in 5. And so for the trees rooted in 3 here, it's trivial. But if we have a larger depth, we will do it for the tree rooted in 3, and so on and so on. So basically every node receives a certificate for the of a spanning tree for the subtrees of the root, so the parent that is just a child of the root, and so on and so on and so on. But we know that we have depth k, so we receive at most k certificates.
So you say that for every graph of tree depth k, there is an elimination tree of depth k, such that for every vertex in this elimination tree, its subtree is connected. That's what you say? And it seems.
What do you mean by elimination tree?
This tree structure that you have behind.
Yeah. So here, what I'm saying is that I can assume that. So basically, I assume that my graph is connected.
But
Again.
look, the subtree of 5 in your example is this? Oh no, it's connected because
It's connected because I have a 1, 5 there. Essentially, if you have no edge between two, so the subtree rooted in 2 and its parent, then it means that 2 can be, you can just push it up one more step above.
I see.
And since I am connected, I know that I have to connect at some point because everything has to be somehow connected to the root.
I see. Okay.
So that's really not the super deep result. But yeah, that's what I claim. Basically, if you have no edge between a subtree and its just parent, you can just move the subtree above in the graph. Okay, and so now maybe the main results we get is that every MSO formula can be certified with big O of log n bits on banded tree depth graphs. And essentially, so we have this Gajarski and Jelini result that ensure that we we have this subgraph that exists, that it's equivalent for every MSO formula on banded shrub depth. But actually, when we read the proof, that's not exactly clear what is this graph if we have just a tree depth partition, and that's not clear neither if it's easy to certify or not. So basically what we did is that we just reproved that for tree depths, which is a weaker result, but we proved that in every graph of banded tree depths, we can find a subgraph that is not too huge, that has banded size in the tree depths and the size of the formula, and that satisfies all the same set of formulas of size at most k. And so we proved that it's equivalent using Ehrenfurt Frese games, and we proved that we can certify this kernel. So that's our main contribution. And since FO and MSO are equivalent for banded tree depths, now this FO results, first order logic result, extends to MSO directly. And basically, let me explain in maybe 1 or 2 minutes how we can construct this subgraph. So we start from the leaves. And what we do is, okay, imagine that I have a leaf. So when I look at depth k, and I have a node of depth, okay, k is 2 things. So let's look at the highest possible depth d, and let's look at some node at depth d minus 1, and assume that this node really have a lot of children. So what I claim is that now if our formula, first order formula of size at most k, then we know that only k of these children will be, so it's enough basically to keep k of these children for our formula. We don't need a huge amount of vertices that are leaves. We just need k of them basically, because if we have more than k, we know that since they are all equivalent, we can replace one by the other for FO. So that's not completely true, because we have to look also at the neighborhood to the previous nodes of our tree, so to the other ancestors of these leaves. But basically, we can just make classes of equivalence or vertices depending on their neighborhood in the list of ancestors. And now if a class of equivalents are more than k vertices, what I claim is that we can remove some of them. We don't need them because they are equivalent, completely equivalent. And since our FO formula is at most k vertices, k quantifiers, we know that we select at most k vertices. And so we can just throw away the other ones. Okay. And so basically we can remove these vertices. And now we can repeat that at the at the depth d-2. Now here, when you look at this vertex, after the removal of these vertices at depth d, it has 3 childs which have exactly the same rooted subtree here. So this node has 3 childs whose rooted subtree is just this node plus 2 leaves attached on it. And again, one of them is useless and I can forget about it. And I can repeat that again and again and again up to the roots. And then we can prove that the number of vertices we keep, so here at the depth d-1, d-2, and so on and so on, we can prove that this number of vertices is bounded by induction. And so that permits to have this subgraph that actually satisfies exactly the same FO formulas of up to k quantifiers. And now, in order to conclude, we just have to prove that we can certify this kernel, and we can do that because basically we can, so this node can check that if these nodes were eliminated, then they really have to be eliminated because I have at least k of the children that have exactly the same type. Okay. And so to conclude my talk, I again want to ask a couple of questions. So the first question is, can we certify banded tree widths? So I think that's not simple, but probably we can use many things. And maybe what we can also try, we didn't really try it, and I would like to try, is try to at least approximate the tree width. So maybe we can't, so if we have a graph of tree width k, maybe we can guarantee that we will find we can't certify that it has tree width k, but maybe we can certify that it has tree width at most, I don't know, 10k. That would be interesting.
I have a
The
question.
other, yeah, sure.
One more question. And what are the methods to show that it's not, that it cannot be certified? I know maybe you mentioned it in the very beginning, but
yeah. So
how could I approach it from the other direction, right? From the other side?
So that's a good question. I'm really not a specialist of that. But I have the feeling that usually the techniques they use are from complexity of communication. But yeah, one of my goals is really to look carefully at these papers I didn't really have tried to read yet, and to understand all the lower bounds results and try maybe to adapt them also, especially for the H minor case. I can hardly believe that it's big of log n.
Okay, thanks.
It doesn't make sense to, when you look at the bounded tree width question, it doesn't make sense to go for to certify if we have a large grid minor.
Yeah, so if you want to prove that your graph does not have banded tree widths, that's easy because exactly you just have to certify a grid minor, and that's easy. But how do you certify that you don't have a big grid minor? That's basically the question. So in order to certify banded tree widths, you have to certify the non-existence of something, and the non-existence of something is much harder. So maybe I can move to my last question because it makes a good transition. So for instance, if you want to certify the existence of a triangle in a graph, that's really easy. You just have to pin 3 vertices and say, okay, I have my vertex x1, my vertex x2, my vertex x3. That's 3 vertices. And so the vertices just check that there are edges between them. But we do not know how we can certify that a graph is triangle free. And so we think that it might, actually the answer to that question might be negative. Maybe that's hard to certify that a graph has no triangle. And why? It's basically the somehow related question of detecting a triangle in the congest model of distributed algorithm, whatever it means. It's a complicated question. So maybe that's a hard question. So yeah, again, certifying that something exists somehow is simpler than certifying that something does not exist. And yeah, two other questions I'd like to mention. So the first one is, can we extend this tree depth result to shrub depths? So that's possible, but yeah, I'm not a specialist of shrub depths, and we had the feeling that for people from this distributed community, if we speak about shrub depth, it will be a bit black magic maybe, and tree depth is a bit easier to understand. So since we had the proof that is completely written for tree depths when we discover what is shrub depth, we didn't try yet to see what happened, but I can believe that it can be adapted, but there are some issues that if it can be adapted, that's not direct. Basically, for shrub depth, you again have a kind of tree decomposition of banded depths, but the problem is that you have. So here, the advantage of tree depths is that you really have vertices on the nodes of your tree, and so that's easy because when some vertices here at depth D want to broadcast information to their parent, they know where to broadcast because there is a natural parent that is that guy. For shrub depth, basically all the nodes are on leaves, and so that's a bit more complicated to know between which vertices you have to broadcast information, because you have no natural vertex to an ancestor to just send information. But I would like to think that it, yeah, I think that it should be doable. Another question is what happened for banded tree lengths. So basically what we did there is okay, we assume that basically there is no long path in our graph. Tree length is a bit like a generalization of caudals. So caudal graph, we assume that all the bags have banded diameter. And so now the question is, can we say something there? And so this question for triangle free, and I think that was, oh yeah. And so of course, if we can certify one of these classes, tree width, shrub depth, tree length, can we certify any MSO formula on this graphs? But yeah, what I want to say is that for tree depths, basically, when we have the certificate for banded tree depths, that's not much harder to have the certificate for any MSO formula. When we have understood how to reduce our graph, we did basically all the work. The certificate is not that complicated to get. So maybe that's the same for all these other widths. I don't know. So thanks a lot for your attention, and